last class, we did double duty on the lectures. Got a lot of work done, did some ice tables. Remember, we did ice tables for weak acids, weak bases, and we also talked about salts and ionic compounds and anions and cations. And sometimes those things can be weak acids or weak bases, but only if they're the conjugate acid or base of a weak base or acid, respectively. And we went over all four of these, all the scenarios that show up here in those previous slides. So, seeing if we remember anything from last time, determine if the following solutions of each salt is acidic, basic, or neutral. So split them into their cation and anion, the positive and negatively charged anion or ions respectively, and figure out if they're related to a strong or weak acid or base. All right, coming back, I'm testing out the new, well, it's not a new feature, but I'm using the pause function so that there's not just big blank voids in the videos. So we want to determine if each of these solutions formed by these salts is acidic, basic, or neutral. So we have to look for conjugate acids and conjugate bases of weak acids and bases. So splitting up sodium bicarbonate, we've got a sodium ion like we might get from sodium hydroxide, is what comes to mind. Sodium hydroxide being a strong base means that sodium is going to be neutral. So the sodium part is neutral, and we also have our bicarbonate or our hydrogen carbonate anion, which we would get from carbonic acid. So if it had one more hydrogen on there, it'd be carbonic acid. Carbonic acid is a weak acid, and so HCO3 minus is a weak base, so overall basic. The other way you could think of it, instead of trying to think back to what you would get, is just add an H or add an OH, depending on if it's positively or negatively charged. That's kind of what we're doing anyway, but slightly different way of thinking about it maybe. And then in B, our positively charged ion here, our cation, is ethyl ammonium. So we've got CH3, CH2, NH3 plus. It's an amine because it's got the nitrogen. And it's got a positive charge. It would have picked up that H plus from an acid, so it's a weak base, or from a weak base. This is a conjugate acid of a weak base. So that's going to be slightly acidic. It can lose an H plus to go back to being ethylamine. And then the other side of the coin, our Cl minus, if we added H plus then we would have HCl, which is a strong acid. And the conjugate base of a strong acid is pH neutral. So overall, that one is acidic. For C, our cation is potassium ion. So we've got K plus why do I keep changing colors? K plus, like from potassium hydroxide, which would be a strong base. And so that's going to be neutral. It doesn't have a strong affinity for hydroxide, or it doesn't have an H plus to give. And then we've got nitrate, NO3 minus. If you add in an H to that, add a proton to that, we've got nitric acid. Nitric acid is a strong acid. And so nitrate is neutral. So overall, that's going to be neutral. Questions so far? All right, and then the last one, our cation is iron 3 plus. Iron 3 plus is a small, relatively highly charged metal. And so that is acidic. And we saw nitrate in the previous example as being neutral, and so this is going to be overall acidic. Some more practice. Which ionic compound forms an acidic solution when dissolved in water? It's not B. It's not C. Yes, it's A. So the two ions across all three of these ionic compounds that will actually form not a pH neutral solution are the ammonium and the hydrogen carbonate or bicarbonate. So those are the two ions that will actually change the pH of the solution. And HCO3 minus, or bicarbonate, can pick up an H plus, which means it's taking an H plus out of solution. It's making an OH minus, or a hydroxide in solution. So it forms hydroxide in solution by taking a proton from water. So that will form a basic solution. Our ammonium, on the other hand, has an extra proton It's the conjugate acid of ammonia. And ammonia is a weak base. And so that one will create a slightly acidic solution. We also have not just monoprotic acids, we have polyprotic acids in addition to mixing acids. Polyprotic acids are kind of like mixing acids, but it's just one acid. So like sulfurous acid, H2SO3. Sulfurous acid can release one of these front H's, one of these protons, as a proton, and produce HSO3 minus, hydrogen sulfide. And our Ka value, a measure of the strength of the acid, how readily that releases, is 1.6 times 10 to the minus 2. Relatively high, but not a strong acid by any means, but relatively strong for a weak acid. And then in the next step, it can release another, its last, hydrogen, as a proton. And that has a Ka value of 10 to the minus 8 instead of 10 to the minus 2. So it's much, much lower. We're going to be releasing a lot less, like 5.5 orders of magnitude less H plus or hydronium. So it's going to be a lot smaller contribution. So it doesn't contribute a significant amount of H plus relative to our first H plus. The reason for these polyprotic acids having separate Kas and the second Ka being much smaller is that our first proton is leaving a neutral molecule. And so the change in, it's not really the change. It's leaving a neutral molecule, so there's less negative charge. We've got something with a 1 negative charge and a 1 positive charge, and those are splitting up, breaking up. And then in the second step, we've got something that already has a 1 minus charge, and we're trying to remove or release a 1 positive charge from that. So this SO3 has a 2 negative charge. It's going to be harder for that H plus to leave. This is sort of a Coulomb's law effect, like we saw in Chem 1A. Stupid nose. So in our first one, we've got H plus leaving HSO3 minus. In the second one, we've got H plus leaving what's essentially SO3 2 minus. And that larger charge makes for a stronger attraction. That's how I think of it, at least. Like if you play with magnets much, if you've got two really weak magnets, like in some of those kinetics, I think that's what they were called, the like magnet building kits with the little metal balls. If you try to remove those magnets from each other, they're relatively weak. If you suddenly get like somebody's fancy neodymium magnet that they're really proud of owning for some reason, and you try to pull that off of even a weak magnet, it's going to be a lot harder to remove those magnets because you've got a stronger magnet now. If that makes any sense to anyone. Hopefully it does. So that's how I would remember that second Ka being even smaller. We can also have triprotic acids, so we would have 3 Ka values, and we would expect that the third Ka value would be even smaller than the second Ka value. And here's a table of some polyprotic acids and their Ka values. In all of these cases, we can see our Ka1 is bigger, because it's a less negative exponent, than our second Ka. And in our triprotic acids, we've got -3, -8, -13. So it's progressively getting smaller at each step because of that change in charge. And for citric acid, it's the same thing, just slightly smaller difference in those Ka values, probably because it's a larger acid. So our Ka gets progressively, weird V, progressively smaller. For each subsequent, each following Ka. So that would be a good trend to know, perhaps. We can also find pH values for polyprotic acid solutions. It's similar to our mixture of acids, but it's a little simpler because we know that we've got 2 or 3 H pluses that are going to be produced. But since they're being produced sequentially, we don't have to choose between which of our acids is stronger and which is going to make the bigger contribution. We know that our Ka1 is always going to be more substantial and form more H plus than our second or third. And the key to this is that our formation of H3O plus in our first step, our biggest Ka, inhibits the formation of H3O plus in the second step. And for the most part, we only care about H3O plus produced by the first Noel. Just kidding, the first Ka. 'Tisn't the season. For Noels. And an exception to that is dilute sulfuric acid. And the reason that we have an exception for dilute sulfuric acid is that H2SO4, that first Ka, is strong. And HSO4 minus is weak. I think the Ka is something like 10 to the -2. Where are those subscripts? Okay, it is a subscript. So it's relatively large for a weak acid. So if we've got a dilute solution of sulfuric acid, our first Ka, our first H plus that we produce, isn't going to completely overpower our HSO4 minus. So our Ka2 will still have a significant contribution. And we'll do an example with that. All right, we want to find the pH of a 0.50 molar carbonic acid solution. So some things that would be helpful, we want to write out our expression for Ka. So our acid dissociation constant, it's like an equilibrium constant, but instead of in our equilibrium, it's different. We looked at them last time. My brain is not working at full capacity. So it would look something like this for our dissociation equation. And that's what it looks like pretty much every single time. And so our Ka looks very similar pretty much every single time. We put our products on top, and our concentration of our weak acid down below. And we should go ahead and use an ice table. I'm going to be using HA as our weak acid and A minus for our HCO3 minus. So our initial concentration of our weak acid, 0.050 molar. And we have effectively no H plus in solution, and we have no A minus in solution. So initially, our equilibrium expression here can only move in one direction. It can only move towards the product side, and that's why our change is going to be minus X for our weak acid and plus X for our H plus and our A minus. So it looks very similar to what we've been doing from last class. There's our equilibrium values, and we can plug in for our Ka1. So we're going to have X squared on the top over 0.050 minus X. And we've got a relatively large difference between our concentration and the magnitude of our Ka1, so let's try the X is small approximation. So we're trying X is small. So we'll get rid of that minus X in the denominator. And after a little bit of rearrangement, X equals the square root of our concentration of acid initially times our Ka1, which is 4.3 times 10 to the minus 7. So X is 0.00014 ... And it'll have units of molar. If we compare that value to 0.05, 0.29%, well below our 5% threshold, so our X is small works really well here. So this X value that we got is the same as our H plus or our H3O plus. So our pH is equal to the negative log of that. So pH is negative log that number should be 3.8. Yahoo! Questions? Why didn't we use our other Ka value? Because that's also going to produce some H+. 3.8 was the correct answer. But I didn't even bother trying our Ka2. Any guessers? It's really small. So in all of our pretty much all of our polyprotic acids, especially if we've got a big difference between our Ka values, we're not going to get a significant contribution from our Ka2. So if we drew out an ICE table for our Ka2, we would be starting with some H+, and that's going to restrict the amount of H+ that we continue to produce from the second Ka value. And it's also really small. So even if we didn't have any of that H+, it should be orders of magnitude smaller, like probably 100-fold smaller than the H+ that we got for our X here. So it wouldn't make a meaningful contribution to our pH. So by just ignoring it, we're making like maybe a 1% error or something like that. Could be even less. But that would be my kind of ballpark guess. We're off by about 1%. We're already doing the X small approximation, so we're off by a tiny little bit as well. Basically, it isn't that important. And we'll write a little note about that. Ka2 is small, we can ignore. The H+ it makes. Like we said in the slides earlier. However, if we've got a dilute sulfuric acid solution, this is one of our exceptions. So we want to find the pH and the sulfate concentration of a 7.5 millimolar sulfuric acid solution. We've got a Ka2 value that's given to us. The reason that we're only given a Ka2 is that Ka1 is strong for sulfuric acid. So if Ka1 is strong, what does that tell us about, what information does that give us or let us access? It completely ionizes. So H2SO4 goes to, no equilibrium arrows here, single directional arrow, goes to produce H+ and HSO4-. So we started with 0075 molar of H2SO4. We've got a 1-to-1 ratio to our H+ and our HSO4-. So we're going to have 0.0075 molar of both of those. And that's important because we've got a Ka2, so we've got an ICE table. So knowing that Ka1 is strong unlocks these initial ICE table values for our Ka2. And our ice table is going to be HSO4 minus, H plus, and SO4 2 minus. Basically just, we'll do this in a different color. Just the things that show up in our dissociation equation for HSO4 minus. Draw in some lines. We'll do capital letters this time. And this is where those initial concentrations from the Ka1 being strong come into play. So this 0.0075 molar for HSO4 minus. And also for H plus. And our initial concentration of sulfate is going to be 0. So like with our previous ice tables with acids, we've got none of one of our products, so only the forward direction can proceed. So we're going to have minus X for our weak acid and plus X for both of our products for our change values. And then for our equilibrium values, we're just combining our initial concentrations and our changes. And then we write out our Ka expression like we have before. So Ka2, in this case, it's going to be H plus and SO4 2 minus on the top, and our HSO4 minus concentration on the bottom. Okay, so we can plug in our values. So for Ka2, 1.2 times 10 to the minus 2, our H plus is our initial concentration plus X. Our concentration of SO4 2 minus is X. And that's going to be all over 0.075 molar minus X. Any guesses on whether we can use our X's small approximation here? So if we try our X's small approximation, the plus X and the minus X will disappear. And so we'll have 0.0075 molar on the top and bottom. So those would both disappear. And so then X would be equal to 1.2 times 10 to the minus 2, which is bigger than our initial concentration. So unfortunately, X is small shouldn't work here. And so we get to instead have fun doing the quadratic equation and multiplication that leads up to that. I was going to be lazy and just write Ka2, but we'll do the whole thing. So multiplying both sides by the denominator gives us this on the left side. What a mess. And we'll have 0.0075 molar x plus x squared on the right side. I'll make all the x's blue. Might as well. So something like that. This is that, 9 times 10 to the minus 5. And we're going to have x squared plus 1.2 times 10 to the minus 2 plus 0.005. This. So that's adding these two numbers. And that'll have an x on it. And then minus that 9 times 10 to the minus 5. And I very nicely, neatly used up all of my space. And we'll plug those into our quadratic equation, or if you've got a poly solver on your calculator, you can just use that instead. So our x1 is that, and our x2 is a negative number. So there's our x1. We're going to be using the positive x value. And so that's going to equal our concentration of SO42 minus. And our 0.0075 molar plus our x1 will turn into a pH value because of magic. Negative log of 0.0075 plus our x value, pH should be 1.94 or thereabouts. Questions?
Is it always going to be the positive value or the x one?
Has to be the positive value, yeah. And the logical reason for that, right, our equilibrium value for our sulfate concentration, one of our products, is going to be equal to x. So we can't have a negative concentration, so it has to be the positive one. Occasionally, sometimes, last class we saw that there are cases where we'll have two positive values, and you just have to plug them in and see what gives you a reasonable equilibrium value, either for H plus or for your anion. Yeah, so I added for the pH, our concentration of H plus overall was down here in our ice table, our 0.0075 molar plus our X value. So that's why I added those together. So this is like basically the one time where our Ka2 actually matters. Other questions? All right, we might want to, sort of like with sulfuric acid, know the concentration of the anion for a weak diprotic acid solution. So in our example above, that was the sulfate. So for our previous example, sulfate. And with some generic forms of our Ka1 and our Ka2, that would be our X2 minus. So this is going to be similar to our first example of stuff with diprotic acids. So for our first step, we're calculating the H3O plus. So we're finding, we do it in red. So we're going to find our H3O plus for our Ka1, and the concentration of HX minus is going to be the same. I think we can all do that, no problem. For finding our X to the 2 minus, we're going to use our H3O plus concentration from the first step, as well as our HX minus that we found in the previous step. For kind of sequential ice tables. And when we're looking for the anion, the Ka2 does matter because that's the only thing that gives us our X2 minus. So we can't just say, oh, well, it's the same as the H3O plus. So we'll get a really small number, usually, for that X2 minus, but it is important. So we do get to do basically 2 ice tables. Twice the ice, twice the fun. Twice the ice, twice as nice. So let's see what that looks like. We want to find the carbonate concentration of a carbonic acid solution in the, for practice, 17.17. That's one that we did, I think, previously. Here we're given a pH value that we can start with, and we are also given our Ka2. So this pH value is really nice. It lets us skip the first ice table. And it lets us skip the first ice table because we can calculate our H3O plus concentration. And if we look at our dissociation equilibrium, our concentration of H3O plus that's formed from this equation is going to be the same ratio as our HCO3 plus, or minus, sorry. So HCO3 minus equals the concentration of our hydronium, or our protons. So that's cool. Love that for us. So we'll do 10 to the minus pH. We do 10 to the minus 3.83. Get a value of 1.47911 times 10 to the minus 4 molar. And now we get to do our ice table. So we've got HCO3 minus, we've got H plus, and we've got carbonate, the thing we care about in this case. Okay, so our ice table, we're starting with concentrations of this 1.47911 times 10 to the minus 4 for our HCO3 minus and our H plus. So we'll put that in both of our boxes for our initials for HCO3 minus and H plus. Our initial concentration of carbonate, CO3 2 minus, is what? 0. And our change values are going to be exactly the same as what we've seen before, minus x plus x plus x, for the same reasons given before. We combine those to get our equilibrium values. Pardon the slide. So our ice table should look like that. And then we get to plug those values into our Ka expression. Our Ka expression, Ka2, it's going to be H plus, not HCO3, just CO3 2 minus on the top, and on the bottom, HCO3 minus. And then we'll plug in some values. So plugging in our Ka2, 5.6 times 10 to the minus 11. We put in our H plus, 1.47 times 10 to the minus 4, plus x. Our concentration of carbonate is going to be x. So we'll add another x on top. And then in our denominator, we have 1.47 dot 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 times 10 to the minus 4 minus x. And this is where the magic happens. If we look at our initial concentration of either of our ions, it's about 10 to the minus 4. Our Ka value is about 10 to the minus 11. Very big difference between those two. And so our X's small approximation should work here. And since we've crossed out the plus x and the minus x, we've got 1.47 times 10 to the minus 4 on top, and we also have it on the bottom. And so we can cross those out. And so our x value then is equal to our Ka2. So x is equal to 5.6 times 10 to the minus 11, which means that the concentration of carbonate is equal to 5.6 times 10 to the minus 11 molar. So thanks to our x is small, and thanks to the fact that we're looking at a Ka2, it's our easiest ice table yet, or our second easiest ice table yet. Woo! So anytime this x is small approximation works for a Ka2, we don't even have to mess around with even taking a square root, which is super cool. Just for our anions. Questions about that fun problem?
And what are you looking for x is small between the two values?
We're looking at the size of our initial concentration and the size of our Ka value, or the size of what we get for x. So in this case, x is 5.6 times 10 to the minus 11. So I'll write in the check for our x is small. 5.6 times 10 to the minus 11 over our initial concentration, which is times 10 to the minus 4. And it's, in this case, 3.8 times 10 to the minus 5%, much less than 5%. So our x is small passes with flying colors. If it was for some reason bigger than 5%, we would get to do the full quadratic mess. All right, dissociation of a polyprotic acid. This is kind of covering the two cases that we looked at where we're looking at the H3O plus, possibly with the goal of finding pH, and or we're looking for concentration of our anion. So in our first step, we do a dissociation. We get a concentration of H3O plus, in this case 2.8 times 10 to the minus 3. If we compare the H3O plus that we get out from the second step, it's 1.6 times 10 to the minus 12, which is so small that it doesn't make a dent in our contribution from our first step. So that's why we've been saying we can just throw out our H3O plus from the first step. So we can ignore this second H3O plus concentration. We cannot ignore the concentration of X2 minus, but as we saw in the example that we just went over, it's equal to the Ka2 if our X is small approximation is valid. So it's entirely possible that you could get this, you could get a question like this on the exam, like this practice one, on our exam 2, where you're given a Ka1 and maybe it's like 10 to the minus 4, and then the Ka2 is 10 to the minus 11, and you might be able to just look at those and be like, okay, our X is small is absolutely going to work here. for our second step, and then just choose the Ka2 value for your concentration of the anion. So that would be a really nice skip. Just basically don't do any work. Just, is X small? Probably. All right, on to the next problem. Okay, now to explain some of the things that we've just kind of brushed over, breezed past. Some hydrogen-containing molecules act as acids and others don't. And some acids are strong and others are weak. And why is that? So for our binary acids, things where we just have hydrogen and one other thing, something that's negatively charged, a nonmetal, if Y is our generic element, in order for this to act as an acid, the hydrogen needs to be able to leave. And it leaves as H+. And so some things that are going to play a role here are bond polarity. So how big is the electronegativity difference? So our difference in electronegativity and our bond strength. The affinity between H+ and Y-, or something thereabouts. So looking at bond polarity, to be acidic, our bond needs to be polarized so that the hydrogen atom is the positive pole. It's going to leave as H+. So we are looking for a strong bond polarity, a Y that has a high electronegativity value. The electronegativity value for hydrogen, I think, is 2.1. So anything that's got an electronegativity value above 2.1 should pass this bond polarity check. So if we look at things that hydrogen can bond to, hydrogen could bond to lithium. If it bonds to lithium, though, lithium is less electronegative. Than hydrogen, and so it's going to take on the positive side of this bond. For hydrogen and carbon, they're not different enough that it forms a polar bond, and so it can't be acidic. I think that's a difference of about 0.4, kind of on the threshold for low end of polar bonds. If we have hydrogen bonded to fluorine, fluorine's our big bully of electronegativity, the 4 value. And so this is going to be a very strongly polar bond. With fluorine hogging the electrons. And so that makes for an ideal situation for hydrogen leaving without any electrons. So that's our first condition that we need for something to be an acid. And our second condition is that we have to have the right amount of bond strength. The stronger the bond between our H and our F, the weaker the acid. If HY bond is strong, so if that bond is strong, the bond is harder to break. which limits the release of H+. So we're going to have slower release of our H+ if we have a strong bond. So like HF, we've got a bond energy of 565 kilojoules per mole, our highest of these three, and that's why it's a weak acid. For HCl and HBr, they're strong acids because they've got weaker bonds. So our weak bonds break more easily. And if we look at just our 6A and our 7A groups, if we increase our electronegativity moving left to right, that's going to increase our acidity because of the difference in electronegativity. So a more polarized bond so our hydrogen is going to carry more of a partial positive charge. And if we move down the periodic table, we're going to decrease our bond strength and increase acidity. Any ideas why that's decreasing bond strength? What's another trend that changes as we move top to bottom? Huh?
Increasing acidity.
That's true. I'm thinking of like a property of the element. There's something else that changes as we move top to bottom. The size. The size changes. How does it change? Yeah. So our atoms get bigger as we move top to bottom, and because our radius for our atoms is getting bigger, but our charge isn't changing, it's like S2 minus, Se2 minus. Se2 minus is bigger, so we've got a larger distance between our H+ and our other thing, in this case, selenium or sulfur. And that increased distance with the same charge means that we've got weaker bonds. So it's a Coulomb's law thing from 1A. So a longer bond is a weaker bond. You could think of it maybe as if you've got a rubber band. The further you stretch the rubber band out, the easier it is to break. If you've barely stretched it at all, you can twang on it, make fun noises. If you stretch it all the way out, you try to twang on it, it might just snap. So that's maybe something you could think about. Oxyacids are another case of acids, or other case of acids. In our oxyacids, we've got hydrogen bonded to an oxygen atom. And these oxygens are bonded to another atom, some generic Y. And again, we're looking for this partial positive being put onto our hydrogen. In order for us to get the maximum partial positive charge on our hydrogen, we want the most electronegativity on this Y value. So now we're thinking of kind of like a tug of war with three people. So we've got the competition between hydrogen and oxygen. That's going to be the same every single time. If we add a really strong person as this Y, that's going to increase the negativity, the electron pull away from our hydrogen. So we're going to improve the partial positive charge on our hydrogen. So a strong pull or a high electronegativity value from Y affects the partial positive on hydrogen. So looking at a couple of cases of this, we've got our different acids with our HO bonds. If we've got iodine bonded, that's got a value of 2.5 for electronegativity. Doesn't pull especially strongly. We've got a low Ka value. If we improve or bump up that electronegativity to 2.8, our Ka value jumps up. If we jump up then again to 3, our Ka value jumps up even more. So increasing the electronegativity of Y increases our Ka value because we're putting more of a partial positive charge onto our hydrogen. We can also change the number of bonds. So looking at our series of perchloric acid, chloric acid, chlorous acid, and hypochlorous acid, so the different oxyanion forms with chlorine. If we have more bonds with our what we're using as Y here, in this case Cl. More bonds there results in a stronger Ka. So perchloric acid, that's one of the strong acids that you're expected to know, is strong. If we remove one of those oxygens, our Ka value drops to 1. If we take another one off, 1.1 times 10 to the minus 2, still a relatively strong weak acid. And then HOCl, hypochlorous acid, is a relatively weak acid. So in this case, those oxygen atoms are grabbing more of the electron density from our Y, and that's going to result in more electron density being pulled from our H+. So we'll draw these as smaller and smaller arrows. The additional oxygen bonds steal more or pull more electron density from the hydrogen. Because this chlorine in the middle has more of its electrons pulled away from it, rather than sitting on it as lone pairs. And didn't quite wrap up the chapter, so we'll finish it up on Wednesday and start the new chapter then too. Any questions before we close?
For the test, you wanted us to review the questions we got wrong. Could I email that to you if I do it on my iPad?
Sure.